Hi everyone, I'm Dihu. In this tutorial, I will give an introduction about self-supervised audiovisual learning. I'm from Gaoling School of Artificial Intelligence, Renmin University of China. I'm so glad to be here. In this tutorials, we will first give an overview about what is and why using self-supervised audiovisual learning, and then give an overview about the recent approaches about how to address the audiovisual learning problems and show what is the inherent self-supervision in audiovisual data. And finally, we will get a summary about what are the core challenges and future directions in this topic. So first, we will give the overview about this topic. So firstly, we show this image about a baby sitting in a sofa and playing a drum. And what can we see in this image? We can see that here there is a drum and there is a baby face and some other things. In the conventional approaches, if we want to identify using the model to identify the object in this image, we should give some bounding box label for object detection, and for providing this bounding box, we should employ some participants to annotation the object in this image. So the model actually is learning from the annotations, not from the data itself. But we can we think give some thought more deeper, and such as or honestly, we can say that in this picture it is not a real world things, because in our real world things, our modality is multiple, such as we can see the baby is playing the drum and we can hear some sound, hear motion, hear sound, and something others. So if we want to understand these scenarios, we should not only depend on the image, we can depend on more modalities. So in this slides, we can see that if we play this video, you can see that the image is moving with the baby is playing the drum, and we can hear some sound, his mother's speech, and the baby's sound. So there are multiple sounds and multiple objects. So in the visual domains, we can see there's a drum, a baby face, and his mom. And the audio domain, we can see the drumming sound and the baby wailing and the mom voice. So here, this is the real world scenarios when our humans want to understanding the scenarios and the information we can learn from. So if we only provide an image, it's not the real learning scenarios. So if we analyze this scenarios, we can see the visual modality and the audio modalities. There is the natural annotation without manual efforts between the visual modalities and the audio modalities, because we can learning the visual information from the sound or learning the sound from the visual modalities. There are inherent correspondence between them. So here is the self-supervised audiovisual learning. We want to find or explore the inherent correspondence between the visual domain and the audio domain, and using the inherent separation from the cross-model modalities, multimodal modalities. We want to using the separation to train our models. So simply, we can see that unlike the conventional unimodal case, video is a rich source of audio and visual modalities, where the correlation between modalities can be used as a separation signal for self-supervised learning. So, as what I said before, we can using the audio to supervise the visual, and using the visual to supervise the audio, or even we can learn from both modalities. So why using self-supervised audiovisual learning, or what's the situation come from? Where does it come from? So it's very simple. Sound is produced by the oscillation of object. So if we play drum, the drum is oscillating and it sounds. It makes sounds. So this property gives us a very important properties. First, it's free. Yes, it's free. It's everywhere. And second, it's reliable because if the object play is sounding, so if it oscillation is always sounding, so it's reliable. Then the third one is pervasive, so we can find the sounding object everywhere. So these three properties help us to understanding the real world scenarios. So there is the inherent scenarios between the visuals and scenes and the soundscapes. So simply we can using what we find the observation from the visual scenes and the soundscape, we can using the correspondence to train the audiovisual networks. So there is a very simple pipeline using the audiovisual correspondence to judge the audio or the image are from the same video or not. In the right, we can see that the temporal synchronization is used to judgment the audio and the image are from the same timestamps or different timestamps. So there are two kinds of audiovisual self-supervision for training the multimodal networks. So in apart from the video level, we can use in the spatial level. In the spatial level, our real world is 3D space, and our sound is a stereo sounds. So if an object is sounding in our real world 3D world, we can in the visual domain we can know how far it from us and where it is. And so in the stereo sound, we can hear and sensing where it from, our behind or our front. So we can using their spatial correspondence for us for navigation or sensing the environment in the 3D space. So here is the 3D space correspondence between the visual and the audio modalities. So here, what we have shown is what is the self-supervised learning, audiovisual learning in this topic, and show what's the self-supervision in audiovisual modalities. So in the next step, we will show how to using the self-supervision in the audio modalities to training our model, and how to explore more reliable self-supervision in these two modalities. So we give a roadmap in this topic. First, I think before 2017, it morely depends on cross-model knowledge transfer. This is using one modality to supervise another modalities. So it's much like a knowledge transfer using the pre-trained visual networks to training the audio networks or vice versa. And in the second step, or in the second stage, we show that we can using the multimodal modalities such as audiovisual modalities. We can learning from the audiovisual data itself. So it is using their correspondence performs analysis in the scene level. So in the present, we can using the correspondence between the visual and audio to perform object level the perception. For it is more precisely for the more than the scene level audiovisual learning. So we can learning to perceive the object or each sound. So here is the roadmap in audiovisual learning. Then we will give an overview about the approaches about the SOTA method in this topic under the roadmap we present. So first we will show what is cross-modal knowledge transfer. So in cross-model knowledge transfer, we think that if we train visual networks on internet, we can learning to classify different objects or different image, such as the car, the baby, the dog. And if we learning from audio network from the audio domain, we can learn to classify different sound in different classes. So if the audio and visual come from the same dataset, or they are described the same video, we can using the image knowledge or visual knowledge to supervise the audio data. It's very makes sense because if the audio and the image from the same video, they are describing the same event or knowledge or object. So we can using the visual knowledge to supervise the audio knowledge. So it's much like the knowledge transfer strategy. So in 2016, uh, the research team in MIT released a simple knowledge transfer for artificial learning. They first train ImageNet scene and place scene on the object for object detection and scene classification. So if we pre-train the visual scene or visual networks or visual recognition models, here we show that we can learn some visual knowledge. So if we download some unlabeled video in YouTube, we can separate the visual information and audio information. If we fit the visual information to the pre-trained visual networks, we can learn some visual distribution for these videos. Then we assume that the audio should take similar distribution in the same scenarios. So you can see that they using the visual networks to extract the visual knowledge, then using the visual separation to training the sound net. So after training the sound net, we can it can learn to recognition or learning some better audio repetition for the sound data. So in the right image, we can see that for the feature evaluation, we can see that SoundNet can provide a much better classification result on the benchmark dataset for sound scene classification. Then we show that apart from the natural things, natural things or natural object sound, we wonder that if one can learning the correspondence between the visual and the audio speech, it's not the natural object sound, it's speech. So it's much like the image captioning, but the text as spoken by the participants. So in this work, the visual knowledge is also using the pre-trained VGG net in offline model, and we using the pre-trained visual net to extract the visual knowledge from the image, and they ask the participant to speak the image caption, and directly training the speech and the image by their similarity to judgment they are from the same video or not, or same scenario or not. Then after training the network, they found that the image and audio spectrogram, here spectrum is an audio, so they found the image and the spectrogram have highly similarity. So such as the image we show here, we can see that. So with the shown image have some grassy, so the spoken language here, the grassy have a higher percentage. And here is the baseball sports, and the baseball here, the spoken speech spectrum has a higher percentage here, the baseball. And further, they using the model to retrieve for image to sound retrieval and show some good results. Mm, further research work is using the audiovisual networks we show here for grid perform a grid over the image and want to know better what's the location of image, the local image, the patch between the image patch between it and the speech signal, and they found much better correlation between image and speech. So in the previous shown research works, we show that we can using the visual knowledge to supervise the audio modalities or model or audio networks. So we wonder that if we can use the audio knowledge to train the image data or image network or visual networks. So here it is. So in this works, Owens considers that we can using the clustering techniques to detect the or to learn the sound event or sound knowledge distribution, then using the clustering result of audio data to train the visual distribution or visual networks. So here is the simple baseline or simple pipeline. Here we can use show that for the right box here we show that we can using the clustering techniques to learning the audio knowledge, then using the clustering result to supervise the visual CNN model for training the visual image. So here is how to using the audio knowledge to train the visual knowledge or visual networks. Here is some result the CNN trained by sound. We can see that if we training the visual visual networks by sound, we can learn that the visual detectors are better than the random one, because we can see that it shows better than the person detectors, text back detectors, baby, and so on. But compare the labeled scenarios, we can see that the detectors distribution trained by sound is actually a long tail distribution, because in the daily life, much sound are from the person or speech, not some other natural object sound are rarely sounded or heard. So it also reflects that the real world sound distribution is a long tail. And then they show that after training the visual networks, we have some neural visualization of networks trained by sound in the left image. And in the right image, we can see that if we after retraining the visual networks, we can using the visual networks as a feature extractor, and for evaluate the feature the networks, and we can using another dataset, image dataset such as VOC or SIGN, and even the Pascal VOC for extracting their features and learning the downstream tasks such as image classification and other tasks. We can show here. We can see some result here. We show here, and if we using the sound knowledge for visual separation pre-training, we can have some better feature, have some good feature evaluation results, and this shows that the image can the sound knowledge can indeed can provide the effective solution for image learning for visual learning. And a more general cross-model transfer framework is published in 2017, and in this works they simultaneously learn the correlation between sound, image, and text. And one modality such as the image network is pre-trained, and it can help train the sound and text if they are from the same source. So here is the more general cross-model transfer networks. And here's some results using the general cross-model transfer framework. We can see that if we input in the left image, if we input an image and in the sound modalities, it retrieve result are barking and barking. It's a dog barking, and the text retrieval result is about the sentence describing the dog, and also in the same domain of visual domain, we can see that the image retrievals are all about dogs. So here is shows that the knowledge transfer is it really helps to the learning performs the model learning in different modalities. So here we have shown the first stage about cross-model transfer, knowledge transfer. This work has shown that if we can really using the correspondence between audio and visual modalities for learning for transfer the knowledge from this domain to another domains. And the next we want to answer that if we will not have the pre-trained model, or we do not have the pre-trained knowledge from a notation or labeled design, or trained from the labeled design, we can learn from the audiovisual knowledge from random wild data set. We want to answer that. So in this slides, we also review this slides. We can see that there is a correspondence between the visible things and the soundscape. We can using the video level correspondence here to training the audiovisual networks without any pre-training on each subnetworks. And here, this pipeline is not using any surprise pre-training, as stated before, such as the cross-model transfer. So in this works, it's published in 2017 ICCV, and it's very simple network or architecture. So it depends on the video level correspondence to judgment whether the image and the audio are from the same video. So after the training using the shown networks in the left, it shows some visual feature evaluation and audio feature evaluation on different data sets. We can see that for the visual feature evaluation is evaluated on ImageNet. We can see that it's beats most unsupervised method in the top one accuracy. And for the audio feature evaluation, we can see that for it shows comparable performance to the human performance on the dataset of ESC 50. And on the DK's dataset, it also shows the best performance, much better than the SoundNet. We recall that SoundNet is pre-trained, it transfers the visual knowledge to the audio modalities. So if we're just learning from the data itself, it even outperforms the cross-model transfer strategies. It's very amazing. So here we shows here the authors show some results about semantic heat map for visualization of a visual concept. We can see that the visual networks actually activate on specific scenarios for some linear cells, such as horizon and railway and crowd. And the audio concept is very the result also shows the audio networks are specifically activated on different audio sounds, such as baby voice, human voice, and others. So here, this works. On the left is using the video library correspondence. So we want to understand. We want to answering that if we can find some better correspondence or some others correspondence between audio and visual networks. So we do audio and visual modalities. So in the left, we can see that the author provide in 2018 proposed that we can use the temporal synchronization to training the audiovisual networks for learning the scenarios. So this work is training to the objective is training the model to judgment if with the audio and visual modalities are from the same timestamp or not. So this works is also without the supervised pre-training. And the objective loss is the contrastive loss, and it depends on the positive and negatives. It want to train the model to learning higher to learn to predict higher similarity between the positive pairs. The positive pair is from the same timestamps, and the negative pairs are from different timestamps. And they also grade some negative pairs, such as the hard negative pairs and super hard negative pairs. So the hard negative pairs are from different timestamps that are far from each other, but the super hard negative pairs are the pairs or the visual pairs are near in the temporal domain. So here this work is depends on the temporal synchronization about audiovisual modalities. So these are two representative networks for self-supervised audiovisual learning for seeing understanding. So sound is produced by the oscillation of sound, and so if the oscillation is a moving or the motion, so the motion is not a static image, but it's a temporal sequence. So in the later works, the different researchers propose that we can using 3D convolution for modeling the temporal or the motion for the visual movements, then we can learn better correspondence between the visual information and the sound information. So in this work, Owens proposed to model the temporal using the 3D convolution to model the temporal motion information for sound producer, and then learn to judgment the motion and the sound are from the same or not. So here it also using the temporal synchronization correspondence between audio and the visual domain. And they also using the trained model for on-off screen speech separation. So mainly in this works, it's using the 3D networks to model the temporal sequence of visual frames. So so in this works, we want to understand that so in the previous that for the baby playing the drum, we can see that this is very complex things or scenarios. In there, we have some different objects and different sounds. So in the previous works, we show that they simply train the model to predict the sound and the image are from the same video or not. But if we have multiple sound in the video and multiple objects, if we simply compare the image and sound, we cannot really answer that they are really correspond or not, because we have different object and sounds in the same video. So we show that the unconstrained visual scenes contains multiple sound maker, and the sound maker does not always produce distinctive sound. And third one is the sound maker may be even out of screen. So we want to learn to align the visual object and the different sounds in the audiovisual in the complex visual domain or video in the complex video, such as the playing drum, the babies playing drums. Then we found that the feature maps of the different visual filters or audio filters are specially correspondence to different visual knowledge or visual object or sound. So we can using their uh, activation to clustering on the in the visual in the spatial domain. Then we can using the feature maps to identify different objects in the feature maps. So here we show that we can using clustering techniques to identify different visual objects or different sounding or different sound produced by different objects. Then we learn to align different sound and visual objects in different groups, such as baby, drumming, and background. Then using the correspondence between the then using the separation of whether the image and sound are from the same video for training the whole networks or the whole models. Then we can learn to identify different objects and sounds. So here we show some results here. We can see that this model has outperformed the human performance by 1 point. And it also shows some good result for sound source localization and audiovisual understanding. Here is one demo. We can see that we can show better results. So here we can separate the baby voice and identify where the baby is. Here is separate the sound of drumming and identify the visual domain where it's drumming, the visual localization. So in this demo, we show that we can better analyze the complex audiovisual scenarios and provide better result for self-realized audiovisual scenarios learning. So here we have shown that we can using the correspondence between the audio and visual to by judging they are learning from the same video or not, that from the same video or not. And then we can find that this depends on the separation to judgment they are from the same video or not. And if you do not want to using the separation of this, can we learn some good knowledge for the audiovisual models? So here there are some recent works about using the aligned audiovisual pairs, not from the negative ones. So here the question is, what if we do not provide the negative samples? So these two works are published in this year, the NIPS, Nano NIPS in this year, 2020, and these two works show that we can learn the audiovisual data itself by not relying on the negative samples, but just relying on the audiovisual, the aligned audiovisual knowledge, the audiovisual modalities. For the first one, in the upper part, it learns to the audiovisual modalities by predicting the categories and then using each modalities prediction to training the other one. This is depends on the clustering and deep clustering, and the shown works in the second one is also depends on the clustering, but it's depends on the optimal transport. But they share similar motivation that using the clustering result to train the model and using the model prediction to learn better prediction such as the pseudo labels, and then training the models such as the EML or algorithm. So here's some results they released, and we can see that they are outperforms the AVTS is the NIPS paper. we have shown that, and this works. The SDC has outperformed AVTS for the downstream tasks about audiovisual audio action recognition. So this works. These two works not depends on the negative samples, but can still learn better performance from the audiovisual knowledge, audiovisual modalities. It shows that we can learn just depends on the video, each video, not from the negative, not explore the negative samples. We can also learn better performance. So it's also third one. The third one or the recent works about self-thrust audiovisual object perception about using the Crossmodel in the scenarios such as the audiovisual from the same video or not. We can learn to identify different objects. So in this, we have shown this video, and we want to answer that: can we learn to recognize objects via their sound? So in this works, it's published in 2018, is using the correspondence label or separation to judgment the video and the image are from the same image, and the audio are from the same video or not, to learn to predict where the sound is produced. So this work has shown a promising result for localization of sounding object. Then the location-based audiovisual similarity actually reflects that where the sound is produced, and we want to and we want to answer that, or we want to question that: how about input different sound? If the visual domain can acted by different sound. So this works in CPR 2018 answers these questions. They input different sounds such as people sound and car sound. The visual networks learn to predict where the sound is come from. So in this works, if we input the people sound, the attention model learns to attend the people areas, and if we input the car sound, the attention model learns to predict where the car is, where the car. And here they show more results in the left figure, such as the location of sounding objects about different sounds. And the first question is about if the input is a mixture of multiple sounds, not a single sound, such as people sound or car sound. It's a mixture of people sound and car sound. It's more real world in our daily life, right? So such as a video you can see here. So in this video, we have multiple sounds such as talking, boating, and streaming, and we have multiple objects: the boat and the people and the trees and so on. So the audiovisual pair is actually a combination of the talking, boating, and streaming. We want to learn the object-like correspondence, not the scene levels, scenarios levels. So how to explore the fine-grained separation if we do not provide this separation? So in this works, the authors these papers or authors show that we can first learn to predict the scene level correspondence, then using the scene level correspondence to predict the object correspondence between the visual domain and the audio domain. So they want to learn the object level correspondence by grid cam or cam techniques, by predicting where the object or where the sound is produced. But actually, we can show the result if the input sound is a mixture about different sounds, such as the first figure, the speech with gunfire is the input sound is a mixture of these two sounds. It can learn to localize different sounds. Not it's very reliable, I think. And then we can show more examples such as training with engines. So in this work, the input sound is not a single sound such as training or engine. It's a mixture of these two sounds. So the model can still predict where this sound come from. It's very amazing. But actually, the object level correspondence is come from the grid cam techniques. So for the grid cam, we actually have to train a classification model. So the classification training is actually pre-trained from annotation label dataset, annotated dataset. So this work also is still relying on the pre-trained object knowledge, such as the internet or audio site dataset. So this works, even though although this work can provide reliable performance or not amazing performance for the complex scenarios analysis, but it depends on the pre-trained object knowledge. So we want to answer that. If we can learn the object correspondence by do not rely on the pre-trained knowledge. We want to answer these questions. So we have a try in this work. This work is published in this year NIPS. So 2020. So in this work, the author first perform analysis about if the learning knowledge from the corresponding or audiovisual localization model, the visual knowledge is can we the learned audiovisual knowledge or the visual knowledge is discriminated is can be discriminately classified. So as shown the right image in the right image. So here we show that the learned knowledge from sound source localization is actually can be classified by different colors. So different colors implies different objects. So we can see that even although we have only the correspondence for between the sound and image, we can also learn the distribution of different visual objects. So depends on the learned visual knowledge, we can learn to build a system or framework to identify different objects. So first by referring the learned object knowledge, then we can using the knowledge to detect different objects, then using the audiovisual correspondence to predict where the sounding object is. So the series still from the correspondence, but in the object category level, the correspondence is depends on the data itself. So here's some results about audiovisual about object localization of sounding object. And here's some results about the sound object localization about synthetic data set. So here is a more real world scenarios about people talking, and in this works the author proposed to using the self-selection about the speakers and their sounds to achieve the multiple speaker separation and the talking head detection and tracking, then the active speaker detection. So the self-selection is very well explored for this task. So in the end, we give a summary about what's the core challenge and future direction in these topics. So we can see that for real world scenarios about audiovisual modalities, we can see different modalities, and we can actually learn the vision from sound, or we can learn the sound from vision using different models. So even more, we can using the data itself, the observations from this data itself for performing audiovisual learning, not from the pre-trained knowledge. So I think the key challenge or the key techniques in self-supervised audiovisual learning is about two. The first one is how to effective modeling for audiovisual scenarios. How it is how to perform very uh, effective analysis about audiovisual scenarios because our daily scenarios are very complex. And the second one is how to explore effective separation for audiovisual data or for audiovisual learning because we only have the separation in the video level. So how to explore the object level correspondence for then help to us to achieve effective audiovisual modeling. So these two models are uh, actually interactive with each other. And then I think so for the future directions is about how to because the audiovisual modalities is in real world is about based on the interaction between us and the environment. So the real learning scenarios about the interaction. So how to perform interaction with the audiovisual environment is one future direction in these topics. And then how to perform high-level semantic scene understanding using the self-supervised audiovisual learning, self-supervised audiovisual supervision to achieve this scene understanding. And the third one is the principle for multimodal learning and how to train it is how to train our audiovisual networks. So here is tutorials and for self-supervised audiovisual learning, and I hope these tutorials will can help to give a better understanding about what is self-supervised audiovisual learning. And if you have any questions, you can send me an email. Thank you very much.